All right, today we're talking about chapter 3, section 7, the elasticity of demand. Now, unfortunately, we're actually gonna have to read all this, only because it really um, the entire section is predicated on this. All right, I know we've had sections so far where we can kind of skim by it, but in this particular case, we cannot. At least we can't skim by it in a good way. So let's go ahead and snip all this. We'll put all this on the notes. Oh gosh, that's a lot of stuff. Okay. Nope, wrong button. Dadgummit. I'll just put that right there. Yeah, there we go. All right, and yeah, this will go on the next page. Last stepping here. I'm pretty sure we skip the proof and we go right to the example. Good. Let's go ahead and snip that as well. All right, so today we're talking about a new concept called elasticity. Now, the the elasticity of demand. And the reason why we have to go over this and read all this bit by bit is because, well, again, like I said, it's needed. So if you're watching this on YouTube, feel free to fast forward or pause it and read it on your own. If you're here in lecture, I feel sorry for you. I'm sorry. But anyway, so the elasticity of demand. A demand function, Q is equal to d of x. All right, so d of x is going to be our demand function. Okay, I guess we can skip this paragraph. But when we talk about the elasticity of demand, it's basically saying, okay, so if we change the value of the price, will the demand go down? Will it go up? Will it stay the same? Will we have a better profit, or will we lose profit? And so, suppose that Clicks Video Games has found that the demand for one of its popular video games is given by this equation, d of x is equal to 120 minus 20x, where q is the number of games rented. Q is the same as d of x. So q is the number of games rented per day at x dollars per rental. So x is going to be the dollar per rental. So Clicks Video Games wants to determine what effect a small increase in the price per rental will have on the demand and on the revenue. So if the price per rental is currently $2, then the demand is, so what we do is we substitute 2 in for x, so it's 120 minus 40, right? 20 times 2 is 40. So we're looking at 80 rentals per day. Okay. Now let's go over to the next page. And so the total revenue will be, if we're charging $2 per rental and there are 80 rentals per day, we're making a profit of $160 per day. All right. Now let's say we raise the price by 10%. All right. So now instead of it costing $2, it costs $2.20. Well, if we raise the price to $2.20, right? Our formula here tells us that there's going to be 76 rentals per day, right? Because 20 times 2.2, or 120 minus 20 times 2.2 is 76 rentals per day. So we're getting 4 less rentals per day. Okay, we're going from 80 to 76, but the revenue, again, we're charging $2.20, and we have 76 rentals per day. Well, that means that we're going to be making a profit of $167.20 as opposed to $160. All right, so obviously, raising the price a little bit, even though we'll have less rentals, we're going to make more money here, and that's of course what we want, right? So now let's suppose that we raise the price to rent up to $5, right? And then the demand, all right, so we put 5 in for x. All right, we're looking at 120 minus 100, and it's 20 rentals per day. All right, so substantially fewer rentals per day compared to when we charge $2 and compared to when we charge $2.20. All right. Well, now our revenue. Will our revenue take a hit? Well, of course it will. $5. We charge $5 per rental, and now there's 20 people renting, only 20. So we're only going to make $100 per day. All right. As opposed to 160 when we charge $2 and 167 when we charge $2.20. So boosting up the price to $5 does not seem like a very good idea. And of course, if we raise that to $5.5 or $5.50, only 10 we can expect only 10 rentals per day. And of course, if we did 10 times 5.5, we're looking at $55. So obviously, jacking up the price is not a good idea. All right. So down here, let's develop a general formula for elasticity of demand. So hopefully you see where the elasticity comes from. When we change the one variable, another variable changes with it. So we begin with the demand function, Q is equal to d of x. For any change, we have the delta x, or in other words, change in x. So the change in x is the price per unit. The percent changed is, and the price is the change in x over x, right? Well, that's it, yeah, change in x over x. So a change in price produces a change, and of course we also have the delta q, the change in q, and the quantity demanded, and the percent change is and the quantity is delta q over q, or the change in q over q. All right, now all that to get to our definition here. And again, all this stuff is mainly just to show how we get to where we get to. But the big deal for this section is the definition here, the elasticity of demand E. So E is going to be the elasticity of demand, and it's just a function. And again, negative here. All right, so note the negative. Hopefully, I won't make that mistake in this particular lecture. Sometimes I'm in a hurry and I forget the negative sign. It happens to everybody. But negative x times the derivative of d divided by d. Okay, so this is the definition that we need, and one moment, let me fix my computer. And this is the one that you need to have memorized and written down, because we're going to be using this quite often. All right, so when we're talking about the elasticity of it, looking over here now. All right, so whenever we have the elasticity be less than 1, we say that is inelastic. So that means a small rise in price will result in an increase in total revenue. And of course, we saw that when we raised the price from $2 to $2.20. When E is greater than 1, the demand is elastic. So a small rise in price will result in a decrease in total revenue. We saw that with raising the price to 5. Although I wouldn't really call it small, huh? All right. And then when E is equal to 1, the total revenue is maximized. This case is called the unit elasticity. So in mathematics, whenever we talk about 1, we usually refer to it as units. Like the unit circle, if you're familiar with it, is a radius. Is a circle with a radius of 1. A unit of measurement would be 1 unit, right? So we usually deal with 1. So whenever the elasticity is equal to 1, we maximize it, okay? And we kind of have that the concept already embedded in us, right? Because we've dealt with maximums and minimums, right? But that's when the derivative is equal to 0. In this particular case, since we're not dealing with just the derivative, we're dealing with the variable times the derivative divided by the function. So whenever we set that equal to 1, we maximize the revenue. So we have the concept in mind. We're changing it up just a little bit now with the concept of elasticity. So in our video game example, the demand is inelastic at $2 per rental, right? Because a small rise in price results in total revenue. But it was elastic at $5 per rental because a small rise in price resulted in a decrease in revenue. Excuse me. And then, of course, that's just reiterated down here with the theorem 11, right? If we are less than 1, we are increasing our revenue. If we're greater than 1, we're decreasing our revenue. And if we're equal to 1, we are maximizing our revenue. So let's put all that to an example here. All right, so we have the demand for video game rentals at Clicks Video Games is given by, we have Q is equal to D of X equal to 120 minus 20X. Alrighty, so we're wanting to find the elasticity of demand as a function of X. All right, so keep in mind, so let's go ahead and put our function up here. So the E of X, so our elasticity, right, this is just the theorem reiterated, is going to be X times our derivative of my function, so d prime of x, and that's not very clear, let's try that again, d prime of x all over d of x. Okay, so obviously looking at this elasticity of demand, right? Well, this is pretty easy. Well, it's just x, right? You know, when we're filling in the blanks here, d of x is pretty easy because it's given to us. The only thing we have to do is find d prime of x. Well, this one is pretty easy. We can do this in our head, right? We just look at the variable. It's just going to be negative 20. So if we're going to fill in the blank here, okay, we have x times, and again, like the derivative of d of x is just simply going to be negative 20, so it's going to be x times a, see, I did it again. Told you, I knew I would. Negative. There we go. So negative, and then we have x times negative 20. Of course, we'll clean that up here in a moment. All over the function of d of x, which is simply 120 minus 20x. All right, so if we clean this up, we end up with negative 20x, so we can, looks like we can do some factoring here. Okay, we have negative 20x, and in the denominator, it looks like we can factor a negative 20 out. Let's go ahead and factor a negative 20 out. Actually, let's just factor a 20 out for right now to make it a little bit easier. Sorry about that. And 6 minus x. All right, so the 20s cancel, okay? And then we have a negative on a negative, so this is going to be a positive. So this function just becomes, let's move it over to the side a little bit so we can have a little bit of room to work. So this function just becomes a positive x over 6 minus x. Okay, and that is A. That is the elasticity of demand. Okay, so B, let's make that A here. B is find the elasticity at x equals 2 and at x equals 5. Interpret the meaning of these values of the elasticity. Okay, so my function is, so my elasticity function is, let's go put this in blue, I guess. E of x is equal to x over 6 minus x. Okay, and if we were to go from here, we wanted to find e of 2. So e of 2, we can do this in our head. 2 over 6 minus 2, which is 4. So 2 over 4 is 1/2. So yeah, so 1/2. And then e of 5, which would be just equal to 5. Alrighty, so looking at this, 1/2 we have greater or less than 1, and 5 is greater than 1. Okay, so what does this mean? Well, whenever it's greater than 1, of course, we see that the revenue decreases, and if we are less than 1, the revenue increases. Of course, all that is noted here. Okay, less than 1, we know that revenue is increasing. If e of x is greater than 1, revenue is decreasing. Okay, so that takes care of B. And C, find the values. Let's go ahead and snip that and put that on the next page. Okay, so again, it's the same concept we've seen before, where we took the first derivative, equated it to 0, and of course, depending on, you know, if we are a local minimum, local maximum, we can minimize or maximize our function. So in this particular case, we're going to take our e of x, which I forgot which was what, x over 6 minus x. So x, let's denote this as c real quick. All right, so x over 6 minus x. All right, and what we're going to do is we're going to equate this to 1. Okay, so let's go back and look at our definition just to really remember this. The total revenue is going to be maximized whenever e of x equal to 1. So whenever we solve for this equation, we'll see where we maximize our revenue. So in order to maximize our revenue, we just have to solve this. And let's do we got x is equal to 6 minus x, by multiplying 6 minus x on both sides. It looks like we're going to end up with x is equal to 3. Okay, so my maximum revenue is going to occur when x is equal to 3. And it says, what is the significance of this price? Well, if we plugged in 3 into this equation, right? 20 times 3 is 60. 120 minus 60 is 60. So we're going to we're going to have 60 rentals per day, but our revenue is going to be, again, $3. Let's do this. Our revenue is going to be that $3 times the 60 that we're going to end up selling, or in other words, $180. Which, if we go back and look at the text here, we saw that if we kept it at $2, we just made $160 per day. By going up just a tad, we go to $167 per day. If we jump to 5 and 5.5, our revenue starts going down. So somewhere between 220 and 5, we end up with our maximum revenue. And of course, our maximum revenue, as we saw in this example, occurs at x is equal to 3. And that's the elasticity of demand. Of course, we have a couple more examples. All right. I don't necessarily think we need this, but we'll put it on there anyways. Yeah, we just have to do this like this. Hopefully you can follow along. And again, this is just a summary of what we did, but I mean, we haven't really done too much to really jog the brain here, so won't talk about too much. Instead, we'll just have some more business models. Alrighty, so this reads, Wayne's Honey Farm sells honey-based moisturizing cream for $12 per jar. At this price, it sells 14,500 jars per month. To see if the price is too high or too low, Wayne's Honey Farm raises the price to $18 per jar. At this price, it sells 10,750 jars per month. All right, so A wants us to find a linear demand function. Okay, so finding a linear demand function, this is going to be one of those things where, if you don't use it, you lose it. But you learned how to do this in your, honestly, I think I teach it in both college algebra and like the intro to college algebra, but we have to figure out a linear model, a linear equation. Okay, so in order to find out a linear equation, let's go ahead and think about how we can do this and kind of go back to a problem from those courses. So let's go ahead and look at the example again. So it reads, Wayne's Honey Farm sells honey-based moisturizing cream for $12 per jar. At this price, it sells 14,500 jars. So that's going to be a point on the graph. So one point is $12 per jar and 14,500. Okay, so that's one point. And the second point should be easy to see as well. If we raise the price to $18, then we're going to sell 10,750 jars. So we put 18 here, and then 10,750. Alrighty. Well, this is now going to be a problem that you might have seen before, and I'll just kind of word it, in the way that a textbook might have worded something like this. So a textbook might have said something like, all right, so find an equation of a line that passes through this point and this point. And that's it. We have to find the equation of a line that passes through both those points. Okay. Well, if you recall, the first thing we need to do is find the slope. Okay. So again, if your eyes are rolling because you're like, oh no, I thought I was done with slope. Bad news. We're not done with slope. Okay. So if you forgot what slope was, slope is m, and then the formula is simply just y2 minus y1 all over x2 minus x1, right? And in this particular case, it doesn't really matter what's y2, what's y1, as long as you're consistent. And yeah, it really doesn't matter. So I'm just going to go ahead and call this point 2, this point 1. So we're going to say 10,750 minus 14,500 all over 18 minus 12. Okay, so 10,750 minus 14,500. We're looking at negative 3750 all over 6. And it does come out to a nice even-ish, well, I mean, it's a nice round number, I guess, negative 625. Okay, so this is my slope, negative 625. And so once we have our slope, if you recall, we also have to use the point slope formula. And the point slope formula is y minus y1, and that's equal to our slope, and we'll just put m for right now, and then x minus x1. Okay. Well, if we fill in the blanks, all right, well, y, again, this y and this x, they stay the same, okay, because that's the whole point of this. Well, we have to choose a point, and it really doesn't matter which point we use. We just have to use one of them. And so let's just go ahead and use the top one. We're going to use a 12 for x and 14,500 for the y. That's equal to my slope, which was a negative 625, I believe. Let's just move this over here. And then x minus, shoot, was it 12? Yeah, 12. That's 12. Okay, so let's clean this up a little bit. We've got y minus 14,500. That's equal to a negative 625. And the 625 times 12 is 7,500. So plus 7,500. Right? And then we're going to isolate the y, and we're changing this from the point slope form to our slope intercept form, which is going to be minus 625x, and then 512, so 2,200, or 22,000, 22,000. All right, so that was just a little kickback, and if you need a refresher on that, obviously I have the other videos on the channel, but um, it says using techniques developed in section R4. So review 4, go back and check it out, and you'll be caught up with this method here. So anyways, this is our equation, and pretty sure that was it for A. Find a linear, yeah, so we have to find the linear demand function, which we did, and B, we're going to find the elasticity of demand. So let's go ahead and put this on the next page, and we'll denote it as B. So B, we need to find the elasticity of demand. Okay. Well, if you recall, the elasticity of demand function was just simply, it was E of x is equal to, and again, I make this mistake all the time, and I have no idea why, and I'm assuming many of you might as well. Always make sure you put your negative sign there. Okay. So it's negative, and then x times, in this particular case, well, we'll just put d prime of x all over d of x. Okay. Well, d of x is going to be this function here. Okay. Of course, we called it y, but that's going to be d of x. That's my function. Okay. So if we were to resolve this, we have negative, and then we have x times, well, what is d prime of x? Well, again, this is pretty easy, right? What is the derivative of this function? Well, it's just going to be negative 625. So x times a negative 625 all over the function, which is negative 625 x plus 22,000. Right. I don't have to put the comma there, but I do sometimes, I guess. All right, so all this comes out to, come on, this ain't too bad. So we've got a negative 625 in my numerator, next 625x, and then my denominator, 5x. Okay, and then we can reduce this. We can factor out a 625, pretty sure. Um, yeah. Hmm. No, can't factor that out. Maybe a 5. No, let's do 125. There we go. Okay. So we can factor 125 out of this denominator here. And if we do that, we end up with a 5x. Well, let's actually not skip steps in case things get confusing. So let's go and put this on the next page and not skip this step. Okay, so I can reduce this. I can factor out a 125. Did I make that mistake again? No, I didn't. Okay. Well, on the previous page, we have the negative here, and then the negative in my numerator. It makes these negatives cancel out and we get to a positive. Okay. So, well, it's all of them really. So let's go ahead and fix that up. Okay. We have negative, 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 and clean this up, and then it should be minus. So I don't need to take that one away. There we go. All right, and of course the negative on the bottom is just connected to this term here, so there's not any cancellation involved. So just to recap, in case I lost anybody. All right, I had a negative right here and a negative right here. Okay, well the negative in the numerator is if I had a a negative negative 4 over 1. Okay, and that's the same thing as saying a negative negative 4, right? And so that's why we can cancel that and cancel these as well. This negative sign is just connected to this term. Okay, we didn't factor out a negative. If for instance, it was something like this, then yes, we could cancel that negative. But since it's attached to just that first term, we're going to leave it alone. Okay, so let's go over this again. Okay. All right, so we're going to factor a 125 out. So 125, we factor out of the numerator. That leaves us with, well, yeah, that leaves us with 5. 1, 2, 3, 4, yeah, 5. And then we factor a 125 out of the denominator. So that leaves us with the same, so negative 5x. And then 22,000 divided by 125, I have 176. So plus 176. And that's how we can get to the point where we cancel out the 125s. So my equation is just going to be my elasticity equation. Okay. So, and again, because I see students do this quite often, these do not cancel out. Okay, because again, the negative 5x in the denominator is just a term into the denominator. It's kind of like if we were to have something like, I don't even know if this is going to be a good example. Let's try 3 plus 9. Okay, so we know this would be 3/12, right? 3 over 3 plus 9, 3/12. Okay, well, that is, 1/4. However, if you were to try and cancel it like, like this, it would obviously be incorrect because then it would turn into 1/9, which is far, far, far from 3/12 or 1/4. So that's why we don't cancel like that. We can only cancel the multiplicative terms. So anyways, I guess that is e of x. So let's go ahead and write this as e of x. And that takes care of B, find the elasticity of demand. So next we want to find E of 12 and E of 18 and interpret the meaning of each result. So finding E of 12 and E of 18, we'll just do this right beneath it. E of 12 and E of 18. All right, all we're going to do is just simply plug in, 12 here, figure it out, and then plug in 18 and figure it out. So let's go ahead and put it into the calculator. Okay, so I get, for E of 12, I get 0.517. Okay, and I'll stop right there. And then for E of 18, I get 1.047. Yeah, okay, 1.047. Okay, so what does this mean? Well, of course, going back to our elasticity um, definition, looking at E of 12, well, we see that it is less than 1, so that tells us that we are um, increasing in revenue. And E of 18 tells us, since it's over 1, tells us that we're decreasing in revenue. Okay, so what I want to do, or so I can kind of derive here, is that the maximum revenue, and of course this isn't part of the lecture or anything, but just thinking about things, we know that the maximum revenue is going to be somewhere between 12 and 18. We don't exactly know where yet, but of course we can figure it out here in a moment. But we know that the maximum revenue is there. Well, we also know how to find the maximum revenue instead of trying to guess, and that is setting E of x equal to 1. So let's go ahead and do that. All right, so this is E of x, setting it equal to 1. We've got 5x divided by negative 5x plus 176 is equal to 1. Right? And let's do the arithmetic. So we're going to multiply both sides by negative 5x plus 176. So we have 5x is equal to negative 5x plus 176. Okay, we're going to add 5x to both sides. So we're going to have a 10x is equal to 176, and we can do this arithmetic pretty darn easily. So x is equal to 17.6. So this is where we have our maximum revenue. When we sell these jars of honey moisturizer for $17.60. And I'm pretty sure you have to do something else. Find the price. All right, so find the price at which demand has unit elasticity. So the price is going to be $17.60. And what does that mean? Well, that's when we maximize our revenue. And just for fun, let's go ahead and maximize the revenue. So if we sold these at $17.60, and we have to go back and look at our original formula. Well, actually, the formula is right here. Okay, so this is our demand formula. So if we substituted in 17.6 right here, let's go ahead and do that just on the calculator. So okay, so that's x time. Let's go ahead and put this on the next page. What was it? I can't just snip it because it'll put it on the page following it, so let's find the equation. Okay, so negative 625x plus 22. So it's going to be, so my revenue is going to be equal to the price that I sell it at times my function there, which is negative 625x plus 22,000. Okay, and if we substitute it in the 17.6, okay, then we have we end up with 193,600. Okay, and if we go back, and so 193,000 is how much we can make, and well, I guess that's about it. There's nothing else too much we can do. Yeah, okay. So we make our maximum profit when we sell these jars of honey for $17.60. Now the next part of this, and the last part for today, um, these particular functions, they're good and all. Where are we at? They're good and all, but they break down when we start talking about the exponential demand. So I'm not going to snip it. We'll just talk about this right here. Looking at the exponential demand function. So the linear demand functions, such as the one we had, they have limitations, okay? And the limitations occur, wouldn't necessarily say at the extremes, but, well, I'll just let the textbook do the talking here. So for example, at a price of $36 per jar using the linear demand function, so if we plugged in 36 into our demand function, we end up with negative 500 jars. And then, although a high price per jar would reduce demand, it's impossible to sell a negative quantity of jars. Okay, so this is where we start talking about the exponential demand function. Now the exponential demand function, we're going to be using Desmos for this, and um, I very briefly glanced at the final exam like a month ago, and I don't remember seeing the use of the exponential demand function. Right? Of course, I didn't think about it at the time, but I don't remember seeing it. But with that said, if this particular function, and of course I'll look at it again, but if this function shows up on the final exam, then we're just going to disregard it because one needs to be able to do our exponential regression. And I don't, I don't, I hate the fact that calculators that can do that in 2021 still cost $150 when you can do this from a free app on your phone or on Desmos, which we're about to do. So if a problem like this is on a final exam, it's not even going to count. But for your homework, obviously it is going to count because you have, Desmos that you're able to use, and so we'll do it this way for today. Okay, it's also pretty cool to know the linear regression and exponential regression, but that's mainly taught in statistics class, so it's not a big deal right now. But anyway, so example 3, use the same data points, which we see here, given in example 2. So using regression, find an exponential demand function of the form of, the form of an exponential function. Well, in order to do that, we have to use a calculator. I mean, I guess we can do it by hand, but it's so very long and tedious. So we're going to use a calculator. And here's how we're going to do the calculator. Right? So again, you're going to be doing this on your homework, so try to pay attention here. All right? So I'm just simply at desmos.com, and from here, what we're going to do is we're going to first move this table, move it here, I guess. All right, and we're going to hit the plus sign here, and we're going to make a table. Okay, so we're going to make a table, and in the table we're going to mark those points that we've seen before, and they're just at 12, 14,500, and 18, and 10,750. Okay, so for some reason it doesn't sound right, so I'm going to go back and look. 12, 14, 5, 18, 10, 750. Okay, we're good. All right, so once we have this table, we have to make a regression on it. In order to do that, you have to input this exactamundo, okay? So you're going to put y1 All right, so real quick, I'm just going to y and then 1. It'll automatically put a subscript for you. Okay, and then I'm going to hit shift tilde, which is the symbol beside the 1. Okay, make sure you put a shift. You hit shift for that. And then you can hit A, E, because A is going to be some variable. E is going to be obviously the exponential number. And then we're going to hit the caret, which is shift 6, and then B, X, and then just the number 1 by itself. Okay, you don't have to put a subscript. So I'm going to do this one more time and kind of reiterate what we're doing exactly. Okay, so for this, they're wanting us to put this in the form. Why does this disappear? There we go. They're wanting us to put this in the form of P naught times E raised to the negative kx power. Okay, and in Desmos, we're going to let A be P naught, and we're going to let B be the negative k. Okay, or not necessarily negative k, but we're going to let B be the k value. Okay, so again, let's go back to Desmos and write it one more time. Okay, so we're going to write A and then E. I'm sorry, we're going to do y1, and let's move this table one more time. There we go. All right, so I'm typing lowercase y, and then I'm just hitting the number 1. No shift. It automatically puts it as a subscript. And then I'm going to hit shift tilde, the button to the left of the 1. So shift tilde. And then I'm going to write A, or type rather, A, E, and then shift 6 for that caret. Shift 6, B, X, and then I'm just going to put type a 1. It automatically will put it as a subscript for you. Okay, so we have A is equal to 26,380.7. So let's go ahead and pretty sure, yeah, we'll put, instead of memorizing it, let's just go ahead and snip this for us. Yeah, let's go ahead and snip that part. And again, these are just the values that we got on this page, well, on the calculator right here. We see we're told that A is 26,380.7, and then B is negative 0.049. Again, the A is the P naught, and the B is going to take the place of the K. All I did was just simply change the values there. Or not values, but go ahead. Um, I can. Yeah, I'll go ahead and do that. Yeah, I'll do that. Um, I also do feel like, saying the shift and stuff really helps. But yeah, I'll go ahead and put this here and put it in the notes for you. And we'll go ahead and rearrange like this. I mean, honestly, that was a very good suggestion. Thank you. Uh, but here we go. So we see that, I mean, obviously, the textbook goes a little 746, whereas Desmos went to just 7, and so forth with the B. But there we see our regression model. And then, of course, going and finding the elasticity, well, this ain't, well, actually, it's not going to be too bad. All right, so let's go ahead and do it, actually. So B, all right. I was a little worried because I didn't feel like dealing with the derivative, but it's actually pretty easy, isn't it? Because all we're doing is taking this value here and putting it out front, and that's literally it. So my elasticity is going to be, let's actually erase this. Okay, it's going to be and then x times the derivative here, and the derivative is just going to be 26, gosh, 2638.0.746 times, so again, if you recall, we're taking this value here and just putting and just multiplying it by the value in front. That's just the derivative. And so it actually doesn't, no, okay. So this is actually one of those cases where you just kind of autopilot through, and I'll tell you what I mean here in a moment. So I was about to autopilot through, but I realized probably shouldn't, and here's why. So my numerator is this, and that's going to be 26380, 26380.746. All right, now we're going to have to actually move this down below. It's going to get very long. Okay, so we have x times 26,380.746. Okay, and then it's going to be that, and then the derivative. We're again one more time bringing this out front, right? But we're not going to multiply it yet. Okay, I multiply the 26,380 by this value on my calculator for a moment, but then I remembered I don't necessarily have to. No, not x. Times e to the negative 0 point. Golly. Okay, so that is my painful numerator all over my denominator, which is just simply the function, which is 26,380 0.746 times e to the negative 0.04. I promise it's going to look so much better here in a moment, and you probably already see it. All right. So something that you can do with these elasticity functions is whenever you, especially for these functions where you do have exponential equations, is instead of, and again, what I was about to do was I was about to multiply these two together and get a number. Okay. But instead, at this point, hopefully it should be obvious now, I can just simply cancel this with this, cancel this with this, and that's it. And so my elasticity equation is just going to be the uh, this times this, and of course it's a negative times a negative, so it's going to be a positive. So it's just going to be a positive 0.04987x, and that's my elasticity equation. And that's B, and C wants us to find the price at X, which so we want to maximize revenue. So obviously what we're going to do is we're going to take this elasticity equation and we're going to set it equal to 1, and we can go ahead and do that, kind of all by itself over here. No, let's just do a new page. Okay. So by setting this equal to 1, so 0.0, let's mark this as C real quick. So dividing both sides by that 0.04987, so it's 1 divided by 0.04987. We end up with 20.05. So we have x is equal to 20.05, and that is where we will maximize our revenue. Is whenever we sell. Are we still on the honey here? I forget. Spent so long on it. Yeah. Okay. So that was the elasticity of demand, and I guess we'll go ahead and snip this as well. I mean, it's the same thing we just did, but there. All right. So just to quickly recap, using a linear model has its limitations because as we saw in the text rather, um, depending on what your values of X are, you end up getting something absurd like selling negative 500 jars, which I guess is giving it away, right? Um, but selling negative 500 jars, uh, if we sell it at $36, it just doesn't make sense. Okay, so therefore we need an exponential function, and of course, like I said, using the regression that we use on Desmos, you can very easily make an equation, and then from there it's just take the derivative and then set the elasticity equal to 1. And I'm pretty sure that ends this section. And there we go. That concludes today's lecture.